Now that we've seen an example of linear approximation, let's talk about the general setup. So in general, you might have a graph of a function, say y equals f of x. And we've seen that you can use the derivative to find the line that is tangent to y equals f of x at x equals a. Now to write the equation of that line, we need to know a point on that line. Well, we kind of already have that. We know that the x-coordinate is a, and since it lies on the graph of y equals f of x, the y-coordinate must be f of a. Furthermore, the slope is given to us by the derivative of f evaluated at the point a. And then using the general formula of y equals m times x minus a plus b, we end up getting that the equation of that tangent line can be written as y is equal to f prime of a times x minus a, and then plus f of a. So this is the equation of that tangent line, and we also call it the linearization of f at a. Now, in my experience, people who try to just remember this formula often end up mixing up some of the pieces. If you know how to write the equation of a line, well, then you already know how to get from this picture to this equation. You just need to know what the point is and what the slope is. So I'd recommend that if possible, you try to think about this in a way that doesn't require you just memorizing this formula. Now, in any case, the point is that what it means for this line to be tangent to the graph at this point, x equals a, is that if you look at points that are pretty close to x equals a, just a little bit to the left or a little bit to the right, you see that the curve and the line are really close together. Maybe to help us, let's give a name to this linearization. We're going to call it L of x. I should emphasize, of course, that L of x will change if you pick a different a value. But really the key idea is that if x is close to a, in other words, if I pick another point here, say x, that is a little ways away from the original point that I picked, well, then plugging x into the tangent line gets you something that is pretty close to plugging x into the actual function. Right? This is what we did in the last example. We had the tangent line to y equals square root of x at x equals 25. And to approximate the square root of 28, which would be f of 28, we instead found L of 28, and that gave us a pretty good approximation. Okay, so this is the general idea of a linear approximation. Let me draw another picture just to introduce another kind of language you can use, the language of differentials. So again, I'm just going to start by drawing a picture, maybe a bit bigger this time. You have some function here. You've picked a point on that graph. You've found a tangent line. So again, we're going to call that y equals L of x. Now let's imagine that you pick another point over here. It's a little distance away from a. So we might call that distance delta x and call this point a plus delta x. Now the original point was right here at a height of f of a. And this new x value corresponds to a new y value, right? F of a plus delta x. And the distance between those 2 points, well, that's a difference of y values, right? So delta y, in other words, is f of a plus delta x minus f of a. Now what we've seen is that for some functions, finding delta y exactly, or finding, say, a decimal approximation for it, can be kind of difficult. So what we did was we used the linearization, and so instead of putting this new x value into f of x, we put it into L of x. So this distance here, between this point up here and this point down there, we're going to call that distance dy. It's not really the change in y, but it's close to the change in y. And actually, we know how to find what that distance is. dy is the vertical distance between 2 points on a line. Well, we know that the slope of that line is equal to the vertical distance divided by the horizontal distance. The horizontal distance was what we called delta x, and, well, we're also going to call that dx. So the slope was the difference in the y values divided by the difference in the x values. And so dy, that distance in the y values, is m times dx. But remember that slope m was really f prime of a. So notice we're doing something kind of funny here. We're taking this expression dy dx, which up until now has just meant the derivative of y with respect to x. And now we're figuring out kind of a way of thinking about dy and dx as quantities all by themselves. So we think of dx as being like a change in x values, and dy is sort of an approximate change in y values given by an equation like this. More generally, what we will say is that if y is a function of x, we define dy to be f prime of x times dx. And so, for example, if y, say, is the function x cubed, well then dy will be 3x squared times dx. And we call this thing, by the way, this dy, this is what we call the differential of y. Not the derivative, but the differential. And this just gives us another kind of convenient language for talking about linear approximation that focuses a little bit more on the change in the output rather than on the actual output itself.